I'm here to do the Iodineclock experiment. So first of all, I started by putting 60 milliliters of warm water in cup A, where I'm going to add two tablets of vitamin C, that I'm going to shake, stir, and this will be our cup A. Alright, well, the goal of this reaction here is to demonstrate how chemistry kinetics work. We could see by changing variance, like concentration and temperature, how the speed of the reaction could be influenced. So after adding the vitamin C in cup A, I'm going to add in cup B 60 milliliters once again, with 1 tablespoon of brown iodine, this is tincture of iodine, adding in the water, and we're going to add 1 teaspoon of our liquid A into cup B. Now if everything works out well, cup B should become transparent. Exactly as predicted. In cup C, we're going to add 60 milliliters once again, 1 tablespoon of hydrogen peroxide, half a teaspoon of starch. I'm using cornstarch. Into cup C with the peroxide and the water, and then that's when the magic comes in play. We pour cup B and C together and wait until they change color. So we're using our timer. Now we wait. After 1 minute 30, the liquid changed from see-through to this bluish color. So as I said, this experience demonstrates reaction rates. So now we're going to try with a hotter temperature of water. I had warm water, now I'm going to do this again with hotter water. And my expectations are that the new reaction will be a lot faster due to the higher temperature will bring up the entropy, and the collisions they'll be direct, and there won't be any recoils in the molecules, letting them react together. So we'll bring the heat of the water up. Right, so this time we're doing the same reaction, but with a higher temperature of water. We're almost boiling. Water's almost boiling. I did all the steps to bring up to cup B and C, where we have to do is mix them together. Alright, getting the timer ready. So, we're gonna mix them. 3, 2, 1. Alright, reaction came to an end. Completely blue, a lot darker than the other one. The other one took 51 seconds to turn brown. That was the first reaction, and to completely turn blue took more than 2 minutes. While this one, in 1 minute, it became blue, almost black. A lot darker than the first one. So as we can see, my hypothesis was right. When we bring the water temperature up, the reaction happens a lot faster due to the higher entropy and the molecules hitting each other harder. Alright, so this time we're proving that bringing up concentrations of reactants will speed up a reaction. So once again, I did step 8. I filled up A, B, and C. Now I'm up to the mixing point. The change that I did, I doubled the quantity of vitamin C. So if we mix both solutions, we start a timer. Alright. 53 seconds. My prediction was right. Bringing up the concentration of the solution does in fact increase the rate of the reaction. Alright, so finally, for the same amount of concentration and same temperature, I've mixed A, B, and C. We're ready to mix again. But this time I'm going to be stirring all along to see if stirring increases the rate of a reaction. So, how can I explain these results? Well, the first reaction that we did, it took approximately 2 minutes to turn blue. After that, we switched. Well, we did the same reaction again, but with higher temperature. So if I were to represent reaction 1 as this is the curve that represents the number of molecules throughout the temperature. So as temperature goes up, the concentration ball, let's say the average, goes up. So if I were to, exactly like I did, bring the temperature up, this ball wouldn't be here anymore, but it'd be like this. And what this does, this line right here is the activation line, if we could call it. How a reaction works is all the molecules after this line react. So then the curve goes back down, and then there's more. So bringing the temperature up brings more molecules to react faster. So this explains our reaction 1. Reaction 2 has the same graph, But this time, excuse me, it's not, I'm sorry, wait. It's not the temperature that goes up, the ball that goes up, it's the number of molecules right here. So the ball goes like this, because there's more molecules in the same volume, and it goes faster, because the amount of molecules that could react is a lot bigger than the quantity we had to start with. So this explains the concentration. Stirring, we saw it didn't affect how the reaction, the rate of the reaction, because both reactions were aqueous-aqueous. The iodine starts solid, and when we mix it with the vitamin C, it becomes aqueous, and this is why the solution becomes see-through with the I-. Mixing them again brings back the iodine in its solid state to let us see it in the water. Bringing a solid into aqueous, stirring makes it go faster, as we think salt and it doesn't influence the possibility of dissolving, but it brings up the speed because of the surface tension. As we could imagine, this is what salt molecules look like. So when we stir, we split these molecules apart, making it easier for the water to dissolve them. But when we have ionic solutions, the dots are so far apart that mixing doesn't influence. It's like if I was mixing this dot. The water is already around it, so mixing doesn't influence the speed for it to react with this one, let's say. If it was solid with all these dots and I wanted to react with this one, of course, I'll say these ones, of course mixing the solution, breaking these apart, and then reacting together would be faster. But in ionic solutions, it's not the case.